Welcome to the next part. Now we are discussing the LC oscillations. A parallel combination of an inductor and a capacitor is, no, is known by the name as an LC oscillator circuit, which produces the oscillations which are called LC oscillations. These kinds of LC oscillator circuits are commonly used in order to produce electromagnetic signals in the transmission towers where antenna has to transmit various kinds of signals into the air. So how does this LC oscillator circuit is able to produce an oscillations of a given frequency that we will understand from the following set of the figures. We are considering an ideal situation where the ohmic resistance present in the circuit is 0, so that there is no loss of electrical energy. So in the figure number 1, we have an inductor and a capacitor connected with each other in parallel. At this stage, the capacitor is fully charged, so that whole of the energy supplied to the capacitor is in the form of electrical energy, and inductor's magnetic energy is totally equal to 0. As soon as the two are connected, because voltage across the inductor is 0, capacitor immediately starts sending its some amount of the charge towards the inductor due to the potential difference. So as this charge is being sent towards the inductor, the charge flows through the inductor in the anti-clockwise direction, thereby setting some amount of electrical current. As the capacitor is discharging slowly and slowly, the current in the circuit is rising, and that rising current is setting up an increasing magnetic field in the inductor. That increasing magnetic field in the inductor, according to Lenz's law, sets up its own induced EMF and induced current in itself, due to which the induced current is start running in the circuit opposite to the current supplied by the capacitor. So current supplied by the capacitor is running anti-clockwise, so induced current is running clockwise. Due to this inductive effect provided by the induced EMF of the inductor, capacitor will take some amount of time in order to get discharged through the inductor. So as the capacitor will now be further discharged through the inductor, in the figure 3 you can see that it is totally discharged, due to which the current in the circuit will become equal to 0, and the whole of the electrical energy in the capacitor, which was in the form of electric field, it will be now stored in the form of magnetic field in the inductor. So in the figure 3, capacitor loses its energy totally, and the same energy appears in the form of magnetic energy in the inductor. Now this magnetic field was due to the current coming from the discharging of capacitor. Now because capacitor is fully discharged, so that current cannot be maintained, current disappears. This means that inductor also cannot maintain its magnetic energy. So what happens, the magnetic field from the inductor starts collapsing, it starts decreasing. As it starts decreasing, you can see in the figure 4, it again puts up a changing magnetic field, due to which an EMF is induced in the inductor. Due to this induced EMF, an induced current also arises, which according to Lenz's law doesn't want the magnetic field in the circuit to decrease, or the current in the circuit to decrease. So by Lenz's law, the induced current in the circuit keeps on running in the anti-clockwise direction. So this induced current keeps on running in the anti-clockwise direction. But when this current is running, this induced current is running in the anti-clockwise direction, it starts charging the capacitor. But in this case, the charging of the capacitor is now in the opposite direction. So you can see in the first figure that upper plate of capacitor was positive charge, but now capacitor's lower plate is now getting positive charge due to the induced current rising from the collapsing magnetic field of the inductor. So after some time, the full magnetic energy of the inductor will disappear and it will now be converted into the electrical energy of the capacitor due to the induced current coming from the inductor. At this stage, when capacitor is fully charged, it will be at maximum potential. Inductor potential will be equal to 0. Again, potential difference will be set up, due to which capacitor again starts sending the charge towards the inductor. But now in this case, this charge is now being sent in the clockwise direction. This charge, as it is flowing through the inductor, it sets up an increasing current. Again, inductor sets up an increasing magnetic field, but in this case the direction of the magnetic field is opposite to the earlier case. It again, due to changing increasing magnetic field, it sets up induced EMF which will oppose the flow of the current discharging of the capacitor, due to which capacitor will take certain time to discharge. So in the figure 7, when the capacitor will discharge itself completely, the full magnetic energy will be appearing in the inductor, which will come from the electrical energy stored in the capacitor. At this stage, when the capacitor is again at zero charge, its potential will be 0. So in order to maintain the energy flow, inductor magnetic field was arising due to the discharging of capacitor. When capacitor is fully discharged, no charge is there to maintain the magnetic energy of the inductor. So inductor again starts sending its energy towards the capacitor by collapsing its magnetic field. As its magnetic field starts decreasing, magnetic flux starts decreasing, it sets up induced EMF and generates induced current, the function of which is to oppose the decrease of the magnetic field according to Lenz's law. So it keeps on sending the induced current in the direction of the actual current, that is in the clockwise direction, due to which capacitor again starts charging, and in this case capacitor is charging again in the actual polarity as it was given in the figure 1. So this completes one complete transfer of the electrical energy and the magnetic energy from capacitor into inductor, and in this one full cycle, one full electromagnetic oscillation is produced, in which each inductor and capacitor charges and discharges 2 times. So in this case, in this way, the electrical energy can be shuffled between magnetic energy between inductor and capacitor to produce the LC oscillations. We can also describe the same thing with the help of the differential equation to find out the frequency of the oscillations produced in this case. Now, using the inductor, the EMF induced across the inductor at any instant, it will be induced EMF across the inductor will be minus L into di by dt. Potential difference across the capacitor at the same instant is equal to Q by C. And according to Kirchhoff's voltage law, the sum total of the potential in a closed part of the circuit must be equal to 0. This means that minus L into di by dt plus Q by C must be equal to 0. Now, because I is equal to minus dq by dt, we know that current is time rate of flow of charge. We have placed a negative sign here, I equal to minus dq by dt, because as the capacitor discharges to send its energy towards the inductor, current in the circuit is increasing but the charge on the capacitor is decreasing. So negative sign is for the decreasing charge. So if we use this value of phi in the above equation, we will have minus L into d by dt of minus dq by dt plus q by c equal to 0. Negative sign cancels. We can write this as L into d square q over dt square plus q by c equal to 0, or d square q over dt square plus 1 by lc into q equal to 0, or d square q over dt square plus omega naught square q is equal to 0. This is the second order differential equation for the LC oscillator circuit, where omega naught square is equal to 1 by LC, or omega naught is equal to 1 over under root LC, which is the frequency of the oscillations produced in this LC oscillator circuit. Linear frequency can be given as f is equal to 1 over 2 pi under root LC. So you can see that the oscillation produced in this case, their frequency purely depends upon the value of inductor and capacitor. So thus, by varying the value of L and C, we can vary the frequency of oscillation. So that's what is also happening in the tuning circuits. The tuning circuits of the radio television sets is also a parallel combination of inductor and capacitor, where when the tuning is being done, we are actually changing the capacitance value. When the capacitance value of the capacitor changes, the value of the frequency of the LC oscillator circuit also changes. So during that tuning time, when we change that value of the capacitance of the circuit, of the LC oscillator circuit, its frequency changes, and this frequency of the LC oscillator circuit, it tries to match with the any of the multiple frequencies which are incident onto the antenna attached with the LC oscillator circuit. So as the resonance between the frequency of the signal received from the antenna takes place with the frequency of the oscillator circuit, the circuit immediately reduces its impedance to its minimum value equal to that of ohmic resistance, and the value of the current amplitude rises significantly. Thank you.